Richard Feynman was one of the most extraordinary scientists of the 20th century. As a brilliant physicist, he pioneered an entirely new area of his subject.
He's discovered a new law of nature. Only very few people did that. The most numerically precise physical theory ever invented.
Yet he scorned the Nobel Prize he received for this work.
I've already got the prize. The prize is the pleasure of finding the thing out, the kick in the discovery.
Feynman's brilliance helped shape history. As a young man, he helped to build the atom bomb, ending the Second World War. And yet, throughout his life, Feynman rejected authority and refused to conform, preferring instead to follow his passions, from bongo playing to biology, from poetry to painting, from computing to cracking safes. Feynman's fascination with the world knew no bounds. And in his dying days as a maverick investigator on the Challenger Shuttle disaster, he confronted the Washington establishment to reveal the truth about what went wrong.
The stuff that I got out of your seal, and I put it in ice water.
Above all, Feynman's infectious enthusiasm for life captivated millions of readers and viewers.
Feynman's been a showman pretty much his whole life.
Any room he walked into, everyone is looking at him. He was the center of attention.
Electrons behave exactly the same in this respect as photons. That is, they're both screwy, but in exactly the same way.
Here, in his own words and those of the people who knew him best, this is the story of the most captivating communicator in the history of science.
But you gotta stop and think about the complexity, the inconceivable nature of nature.
When my mother was pregnant first, my father said if he's a boy, I want him to be a scientist.
Richard Phillips Feynman was born on the 11th of May 1918 during the Depression to working-class parents living in the outskirts of New York.
Even when I was a small boy, Papa used to sit me on his lap and read to me from the Encyclopedia Britannica. And we would read, say, about dinosaurs. They would say something like, this thing is 25 feet high, and the head is 6 feet across. And he'd stop always and say, let's see what that means. That would mean that if he stood in our front yard, he would be high enough to put his head through the window, but not quite, because the head is a little bit too wide. And it was very exciting and interesting to think that there was animals of such magnitude, and that they all died out. And at that time, nobody knew why. So that's the way I was educated by my father.
By the age of 10, Richard had his own science laboratory at home, where he tinkered with old radios and experimented with physics.
He hired me for 4 cents a week as his lab assistant to amaze his friends. You know, a spark gap with voltage against it? And if you put your finger in, you get a shock. It was my job, as part of my 4 cents, to put my finger in the spark gap for his friends' amusement.
Their father, Melville Feynman, worked for a company which made uniforms. This exposure to the military led to a strong rejection of authority, a value he instilled in his son.
One of the things that my father taught me was a disrespect. You'd open a picture in the New York Times, maybe it was a general, and he'd say, now look at these humans, he'd say. Here's one human standing here, and all these others are bowing. Now what is the difference? Why are they all bowing to him? Only because of his name and his position, because of his uniform, not because of something he especially did.
At the age of 17, Feynman won a maths competition in New York, and it became clear this was a subject in which he was greatly gifted. In 1935, he was awarded a place at the Massachusetts Institute of Technology, MIT. But away from home, for the first time, he was going to miss more than just his family.
She was very beautiful, Arlene Greenbaum, the most beautiful girl on the beach. She had great dimples and long hair down to here when she unbraided it. Oh, we loved her. They were not officially engaged. She was only 15. She was sweet. We all loved her. She loved all of us.
From MIT, Feynman moved to Princeton, achieving full marks in the maths and physics entrance exam, an unprecedented feat. But back home, things weren't as perfect.
The family went away for a spring vacation with Arlene. We went swimming, and my father saw this lump on Arlene's neck and said to her, "What is that?" And she didn't know, but she went to a doctor, and it was the tuberculosis. We were all heartbroken. It was before there was any medicine for it. And although she was sick and dying, he married her because he wanted to take care of her. It was very hard on my mother because she was afraid he would catch tuberculosis. But my mother wasn't given a choice.
The couple braced themselves for life in the shadow of TB. But another menace was about to disrupt their time together. Just months before Richard and Arlene were married, America was drawn into the Second World War, following the bombing of Pearl Harbor. Feynman was asked if he wanted to join a top-secret project based in a government laboratory at Los Alamos in New Mexico. Code-named Manhattan, its objective was to build an atom bomb. The fear was that Germany would invent such a terrifying new weapon first and use it to win the war.
There was nothing that I knew that indicated that if we could do it, they couldn't do it, and therefore it was very important to try to cooperate.
Germany was the center, the intellectual center of theoretical physics. They knew the power of this, that if Germany got this first, we have to make sure that they don't rule the world.
I felt I should do in order to protect civilization, if you want.
Feynman became a member of the Manhattan Project at Los Alamos. Here he joined some of the world's finest physicists, pooling their combined brain power to try to create the bomb.
Oppenheimer was in charge of the scientific or engineering side, and he was quite a heavyweight. Fermi, Niels Bohr, the big names of extremely high level.
Despite being surrounded by extraordinary physicists, the challenge of developing an atom bomb so quickly was an enormous undertaking. One fundamental problem was the sheer volume of calculations required. Without computers, it had to be done manually, slowing progress enormously. That was until Feynman arrived.
He found a way to get calculations going in parallel, still manually, still each person doing one operation at a time, but working in parallel and then having the parts of the calculation come back together later, so that 3 problems in 9 months got turned around to 9 big problems done in 3 months.
I put on the blackboard a challenge. Can we do it? To the boys. They all start to go, yes, we'll work double shift, we'll work overtime, we'll try it. As a result, we did problems nearly 10 times as fast.
He somehow got this team of human computers to work at an inhuman pace and got things to roll. And that was when his scientific seniors, the big shots of science at that time, first became aware of this fellow.
Despite being a key member of the most secret government project of the war, Feynman's streak of maverick mischief was never far away.
So I used to pick the locks all the time and point out that it was very easy to do. And every time we had a meeting of everybody together, I'd get up and I'd say that we have important secrets and we shouldn't keep them in such things. We need better locks.
Between safe-cracking and doing physics calculations, the pace of life at Los Alamos was relentless. But for Feynman, it was a welcome distraction. In a sanatorium nearby, his wife Arlene was confined to her bed, slowly dying of her disease.
At that time, dry climates were believed to be good for tuberculosis. So although he was at high altitude, she was at a lower altitude in a hospital. I remember the day she died. She was 25. He was 27. He was brokenhearted.
Then, in the aftermath of his grief, Feynman was forced to confront the reality of what he had helped create.
They gave out dark glasses that you could watch us 20 miles away. They're going to see a damn thing through dark glasses. When I figured the only thing that will really hurt your eye, bright light never can hurt your eye, it's ultraviolet light that does. So I got behind a truck windshield so that the ultraviolet can't go through glass, so that would be safe. And so I could see the damn thing. I'm about the only guy in the world who actually looked at the damn thing in the first Trinity test.
Three weeks later, America prepared to detonate a second atom bomb. This time, it wasn't a test.
He had been expected to go as the scientist with the first flight. But the bomb was so successful, they decided they didn't need a scientist. So he did not go. Otherwise, he would have been in that plane.
The bomb exploded above the Japanese city of Hiroshima on the 6th of August 1945. It killed more than 80,000 people. 3 days later, a second bomb was detonated at Nagasaki.
It was a very considerable elation and excitement, and there was kind of parties and people got drunk, and it would make a tremendously interesting contrast of what was going on in Los Alamos at the same time as what was going on in Hiroshima.
Feynman was deeply disturbed by the knowledge he had contributed to the deaths of so many.
He had had this great triumph on the technical level at Los Alamos, and then, of course, a terrible letdown afterwards, having run this tremendous race, and then at the end of it concluded that it wasn't, in fact, worthwhile.
In the months after this double trauma, first losing his wife, then realizing the destruction he'd helped unleash, Feynman was thrown into darkness.
Maybe from just the bomb itself, and maybe for some other psychological reasons, I had just lost my wife. I was really in a kind of depressive condition.
In the autumn of 1945, Feynman was invited to become a professor in the physics department at Cornell University. But he was still shaken by the events of the summer.
They expected me to be wonderful to offer me a job like this, and I wasn't wonderful. I thought to myself, I haven't done anything important. Well, I'm never going to do anything important. But I used to enjoy physics and mathematical things, and because I used to play with it. It was never very important, but I used to do things for the fun of it. So I decided I'm going to do things only for the fun of it.
While Feynman was rediscovering the fun in physics, science was in crisis. For many years, new discoveries about how atoms behave had been throwing physics into turmoil. Old assumptions about the world were being proved wrong. This new problematic area of physics was christened quantum mechanics.
Quantum mechanics, in a lot of ways, was the most profound psychological shock that physicists have ever had in all of history. Newton was not right. You can know everything there is to know about the world, and yet you cannot predict with perfect accuracy what will happen next.
Quantum mechanics had revealed the problems of accurately predicting how atoms and their electromagnetic forces would behave. And because these are the fundamental building blocks of nature, it threw everything else into doubt too.
Everything that happens around you, other than gravity, all the immediately experienceable parts of the world are electromagnetism at work. When two atoms get together to form a molecule, that's electromagnetism. So all of chemistry is electromagnetism. And if that means that all of chemistry is electromagnetism, then guess what? All of biology is electromagnetism. Literally everything around us is a manifestation of electromagnetism one way or another.
A new field called quantum electrodynamics, or QED, emerged to try and make sense of electromagnetism and subatomic matter. Sometimes QED seemed to work, but other times its predictions were way off.
It was all crazy. It didn't make any sense. It gave you infinity. Infinity is not an answer. Nothing is infinity. You don't measure in the lab infinity. You get a finite answer. You can't have your basic fundamental theory of physics give you infinity.
These predictions of infinity were stumping the smartest physicists on the planet. Even the father of QED, Paul Dirac, was foxed.
When I was a kid, I read Dirac's book, and he had these problems that nobody knew how to solve. It was described there. I couldn't understand the book very well because I really wasn't up to it. But there, in the last paragraph at the end of the book, it said, "Some new ideas are here needed." And so there I was. Some new ideas were needed. Okay, so I started to think of new ideas.
Perhaps, typically, Feynman's inspiration for his new ideas was unconventional.
When I was eating lunch, some kid threw up a plate in the cafeteria, which has a blue medallion on the plate, the Cornell sign in the cafeteria. And as he threw up the plate and it came down, it wobbled and the blue thing went around like this. And I wondered what the relation was between the two. See, I was just playing, no importance at all. So I played around with the equations of motion of rotating things. And I kept continuing now to play with it. This rotation led me to a similar problem of the rotation of the spin of an electron, according to Dirac's equation. And that just led me back into quantum electrodynamics. Everything just poured out. It's just like taking a cork out of a bottle.
Inspired by the spinning plate, Feynman realised that the fact the equations resulted in infinity didn't mean they were wrong. The problem just needed to be looked at from a new perspective.
Turns out that kind of challenge was perfectly suited for someone like Richard Feynman, who, surprisingly maybe, didn't like to speculate. He wasn't the kind of modern physicist that we celebrate who's always coming up with a new theory of the multiverse or forces of nature or whatever. He really liked to work in the context of things that were supposed to be understood and just understand them better than anybody else.
To work around the infinities in QED, Feynman came up with a truly revolutionary idea. It was such a strange solution, not even his sister, by then a physicist herself, recognised it as serious work.
Richard said to me, "Would you go in the room and get my papers? I want to start working and my papers are in there." So I went in the room and I looked, there was no mathematics, there was these silly little diagrams. And I came out and said, Richard, I can't find your papers. It's just these kind of silly diagrams. He says, that is my work.
The simple little diagrams Feynman had invented were a brilliant way to sidestep the complicated calculations required for QED. They were a sort of shortcut, allowing him to avoid the infinities and make meaningful predictions about the world.
He saw that there was actually a sort of pictorial way of thinking about these pictures, these equations. You could associate a little cartoon, a little Feynman diagram, as we now call them, to every one of these terms in the equation.
Other people would have to work for months, and he would get it in an afternoon. And eventually that's what got his ideas noticed, because he's getting the right answer and he's doing it much simply, even though no one understood what he was doing.
It turns out to be so useful that now we're applying it to completely different fields that aren't particle physics at all. When we look at the evolution of galaxies and large-scale structure in the universe, we're finding that Feynman diagrams are a helpful way of calculating those quantities as well. Quantum electrodynamics, which is the theory that Feynman put the finishing touches on, is the most numerically precise physical theory ever invented.
In recognition of this work, in 1965, Feynman was awarded a Nobel Prize for physics. He shared it with two other physicists, Julian Schwinger and Shinichiro Tominaga, who were also working on the same problem.
Was it worth a Nobel Prize?
I don't know anything about the Nobel Prize. I don't understand what it's all about or what's worth what. And if the people in the Swedish Academy decide that X, Y, or Z wins the Nobel Prize, then so be it.
No, I think that it was entirely right and proper. It was one of the best earned Nobel Prizes there ever was, I would say.
I don't see that it makes any point that someone in the Swedish Academy decides that this work is noble enough to receive a prize. I've already got the prize. The prize is the pleasure of finding the thing out, the kick in the discovery, the observation other people use it. Those are the real things. The honors are unreal to me. I don't believe in honors. It bothers me. Honors bothers me. Honors as epaulets. Honors as uniforms. My papa brought me up this way. I can't stand it. It hurts me.
In 1959, on a trip to Europe, Feynman met Yorkshire woman Gwyneth Howarth. A year later, they were married. Back in California, now professor of physics at Caltech, Richard and Gwyneth started a family.
I got a kick when I was a boy of my father telling me things, so I tried to tell my son things that were interesting about the world.
He was an excellent father, always up to explain things or do things, and we would go on walks after dinner, my father and I, and talk about things, and it was, it was wonderful and delightful. I'd ask him about things, and he'd try to explain them. Physics and math and history and politics and science fiction and life, the universe, and everything. I'm very lucky that I got to do that 2 or 3 times a week. Say, let's go for a walk. Sure.
Growing up with Richard Feynman as your dad was never dull, particularly if you were his teenage daughter.
My parents ordered a car, a van that we could all go camping in, and they had it painted, which was so odd because they weren't like this at all. Father may have been immune to embarrassment, but I certainly was not. And they had, the diagrams painted on it.
So most people thought they were Indian designs, but I remember once we'd just gone to McDonald's and we're in the parking lot and walking out to the car, and someone asked us, "Why is your van covered in Feynman diagrams?" My mother says, "Because we're the Feynmans."
Feynman's reputation as a communicator of science was spreading around the world. In the early 1960s, he began presenting lectures for the public, which were televised.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Caltech invited him to rewrite the physics curriculum for undergraduates. His new course, spanning the entire history of physics, became known as the Feynman Lectures.
All these lectures had a certain amount of excitement and an element of what you might call solid showbiz demonstration.
I'm sure you're all familiar with the joke about the fact that the average family in the United States seems to have 2.5 children. It doesn't mean that there's a half a child in any family whatever. The children come in lumps.
He was very visual, he told jokes, he had a unique way of explaining things. Sometimes that was a slight problem because he was so engaging that you would walk out of a lecture thinking, well, that all made complete sense. But of course, 5 minutes later, you couldn't really remember all the connections. You know, you were just swept along by Feynman's personality, by his humor, by his analogies.
Graduate students started idolizing him. But certainly by the 60s, he was, and his course here at Caltech was very famous.
Outside science, Feynman's interests were also flourishing. He'd become an accomplished bongo player, and he developed a love of painting and drawing, based on a close friendship with renowned Californian artist, Jariah Zorthian.
Gerard, he said, you don't know a thing about physics, and I don't know a thing about art, and yet we both admire Leonardo da Vinci. What do you say we become two Leonardo da Vincis? He said, one Sunday I will give you a day of physics, and the following Sunday you give me a day of art. When he started, he was absolutely an amateur. I mean, you know, just very, very crude.
He drew a picture of me when I was young and very fidgety, and he just has, you know, he just has my head, some hair, and then like my hands up here. So clearly I was kind of like, oh, I don't really want to do this. It's pure with his, that he can see the gesture.
I think he maybe got a kick out of working with his hands, but particularly the pen, and doing features of people.
In the end, he became a very accomplished draftsman.
So enthusiastic an art student was Feynman that he took to spending time in Giannoni's, a strip bar in Pasadena. Here he divided his attention between sketching the girls and solving physics equations.
Other physicists couldn't understand it and say, you know, Feynman is supposed to be a physicist, and he is a brilliant, brilliant physicist, and we need his input very often in Caltech. We need him to talk to us about physics. But what does he do? He goes off and spends all this time with go-go girls, bongo drummers, and artists. He wastes so much time on people. I don't see what they give him. But I think that Feynman got a lot out of people, and I think it enriched his life.
In the 1960s, Feynman took a sabbatical year, but instead of heading for a different physics department the other side of the country, he simply crossed the Caltech campus to study an area which had long fascinated him: viruses. During this time, he also became fascinated by the social structure of ants and enthralled by the potential applications of nanotechnology.
I think in the long term of what he wanted to be doing this year and next year, he would think about figuring out some secret of the universe. But in terms of day to day or hour to hour, he was always guided by what seemed interesting and fun, and just sort of an intuition for the right thing to work on.
In the early 1980s, his son Carl's budding career in the emerging field of supercomputers proved irresistible. He signed up for a summer job at Carl's startup company in Boston.
We were a bunch of MIT students starting a company. So the first day we start the company, I get this knock on the door. I open the door.
And he showed up and he said, Feynman reporting for duty, what should I do?
Salutes. I think, uh-oh, I haven't figured out what I'm going to do with this guy. I mean, I've got a Nobel Prize winning great physicist, and I sort of had a quick meeting and trying to come up with some project that was worthy of Feynman.
So some people went off and came back and said, we want you to think about applications of our parallel computing.
The application of parallel processing to quantum chromodynamics.
I said, no, come on, that's nonsense. What do you really want me to do?
And I said, well, actually, we don't really have any pencils or paper.
He said, right, I'll go out and buy some.
So his first duty was to go out and buy the stationery for the company, all the paper clips and pencils and so on. That was his first assignment.
Thinking Machines, as the company was called, would go on to become a major player in the world of parallel supercomputing, with Feynman applying his methods of shortening calculations developed in the 1940s to the new digital age. And as always, working with Feynman was filled with welcome distractions.
We both liked spaghetti because it was easy to cook. And I asked him why it was that when you broke a piece of spaghetti, it often broke into 3 pieces instead of 2. You should try it. It really does. So, of course, he came up with a theory of it immediately. But instead of being satisfied with it, he constructed an experiment to see if the theory was true, which involved slowly moving the spaghetti off the end of the table and breaking it at different lengths. And then that theory was clearly wrong, and he came up with another theory, and then each theory would lead to another experiment. Actually, by the time the evening was over, we had broken spaghetti all over the place, and we still didn't know why spaghetti broke in 3 places.
This playful curiosity, coupled with the anti-authoritarian values instilled by his father, frequently led Feynman down a mischievous path.
He's just so funny and irreverent, and you have to kind of look at that picture a few minutes and think, oh my gosh, he's really, making nice little horns. Important people, oh yes, I think now would be a great time.
He didn't need the external validation of having everybody respecting him all the time, because he respected himself. He knew he was an extraordinary person. And if he came off as kind of a doofus to some guy that he doesn't know, it's okay, because he knows inside that he's a man of substance.
In 1984, Feynman collaborated with his friend Ralph Layton on a humorous book of anecdotes from his life.
I opened the safes, contain behind it the entire secret of the atomic bomb.
It was kind of accidental how the books caught on. The publisher released the first one, Surely You're Joking, Mr. Feynman, in January of 1985. And the edition was like, I don't know, 2,000 copies or some low number. And in January, and I was thinking, January? The whole holiday season is over. Who's going to buy a book in January?
But people did buy it. And Surely You're Joking, Mr. Feynman quickly became a bestseller. It remains to this day one of the biggest selling science books of all time.
I do remember coming down one evening and seeing him just, giggling and clearly enjoying the book that he was reading. And I sort of looked, what are you reading? And he held up the book so I could see that it was his own, Surely You're Joking. And he said, such a character. Freely admitting that, yes, he was laughing at his own history.
The book vividly captured Feynman's worldview, the sense of curiosity and fun guiding him through life. It was an approach he communicated to an even bigger audience through a series of BBC documentaries broadcast around the world.
I have a friend who's an artist and has sometimes taken a view which I don't agree with very well. He'll hold up a flower and say, look how beautiful it is. And I'll agree. And he says, you see, as I as an artist can see how beautiful this is, but you as a scientist, take this all apart and it becomes a dull thing. And I think that he's kind of nutty. First of all, the beauty that he sees is available to other people and to me too. I believe, although I may not be quite as refined as aesthetically as he is, that I can appreciate the beauty of a flower. At the same time, I see much more about the flower than he sees. I could imagine the cells in there, the complicated actions inside, which also have a beauty. I mean, it's not just beauty at this dimension of 1 centimeter, there's also beauty at a smaller dimensions. The inner structure, also the processes, the fact that the colors and the flower evolved in order to attract insects to pollinate it is interesting. It means that insects can see the color. It adds a question. Does this aesthetic sense also exist in the lower forms? Why is it aesthetic? All kinds of interesting questions which the science knowledge only adds to the excitement, the mystery, and the awe of a flower. It only adds. I don't understand how it subtracts.
Most people have a few stories, don't they? You and I might have like 3 or 4 stories to tell. And some people have, 10 or whatever. And Feynman had, I don't know, hundreds. Feynman was so mesmerizing. I think Chris Sykes in his documentaries captured Feynman how he was. He takes enormous pleasure in finding out about things and exploring life and everything it has to offer. But more than that, he takes tremendous pleasure in telling you about it.
Yeah, I think he was pleased with how it worked out, that he was able to communicate with so many people, sort of his view of the world and of nature and so on.
When I was a student at Caltech, I went up to Feynman's door and I knocked on it, and the door opened, and I explained that my mother had watched this program about him, thought he was interesting. She had no science background, and I said, do you think you can write to her? Because maybe I'll have a better chance of teaching her physics. And Feynman did write to her. He wrote a letter in which he said, Dear Mrs. Chown, ignore your son's attempts to teach you physics. Physics is not the most important thing. Love is. So, I mean, it kind of backfired. I got the greatest living physicist at the time telling my mother that physics was not important, that love was the important thing.
Through his films and books, Feynman had touched the lives of millions. Yet, there was something all this success and recognition couldn't alter.
I did a lot of running. And Feynman thought, gee, that's a healthy thing to do, so he started running too. And when you start running regularly, you lose weight. And Feynman suddenly noticed that one side kind of bulged out.
They discovered a big mass in his abdomen, and he came home and reported that it's the size of a football. It's consumed one whole kidney. So, well, I went to the medical library, I looked things up, and I figured there's about a 30% chance it'll kill me. So, not the kind of thing you want to hear from your father, but exactly the kind of thing he would say. And he sort of quit working at that point because, surgery and chemotherapy and so on, it's a full-time job.
One day, his secretary, Helen Tuck, called me up to tell me that Dick had cancer and he was going into the hospital for an operation the following Friday. And it was a very dangerous operation, and it was not assured that he would survive it. I promised not to tell anyone, and he didn't know that I knew. And I told him somebody had found an apparent error in a calculation that we had done and published together. And so on Monday morning, we met in my office, and he sat down and started working. And he was consumed by it. All of his energy, all of his attention was devoted to solving this problem. And we worked on it all day long. And finally, at 6 o'clock in the evening, we decided that the problem was intractable. It couldn't be solved. We couldn't figure out what the answer was, and we gave up. And we went home. 2 hours later, he called me at my home, to say that he had solved the problem. He hadn't been able to give it up. He hadn't been able to stop working on it. And finally, he had found the solution, and he dictated the solution to me over the phone. He told me what it was, and he was exhilarated. He was absolutely walking on air.
Feynman would recover from this first operation for cancer, but the disease would never completely go away, and he would always be living under its shadow.
We have main engine start, 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Roger, roll, Challenger. Good roll program.
In January 1986, NASA launched its 25th Space Shuttle mission. It symbolized a new era of spaceflight by adding a school teacher called Krista McAuliffe to the crew.
65, final. CDL confirms, follows. Thank you. Challenger, go at throttle up.
I was in social studies, and I think we were taking a test, and the teacher came in and said, "We've had a horrible accident."
Flight controllers here looking very carefully at the situation. We have no downlink.
And then coming home, and my parents had already seen it, and which was unusual because they didn't really watch TV.
Watch your data carefully.
Take hard copies of all your displays. Make sure you protect any data source you have.
The loss of their space shuttle and its crew of 7 live on TV shocked America. The country was thrown into mourning.
Our nation's loss is first a profound personal loss to the family and the friends and the loved ones of our shuttle astronauts.
But there was one question everyone wanted an answer to. What had gone wrong? A presidential commission was hastily put together to find out, but it was comprised largely of space industry insiders with close ties to NASA. Someone independent with unimpeachable scientific credentials was needed.
I have a policy practically of never going near Washington. And I called up various friends of mine who were connected to the space program one way or the other and tried to ask them if they didn't see whether I should go or somebody else could do it just as well.
His friends said, "Dick, you gotta go, because you're the only guy who can cut through the bullshit."
He asked me what I thought he should do, so I just asked him, "Well, do you think it's an important problem?" He said, "Yes, he did." I said, "Do you think you can make a difference?" And he said, after a while, I said, "Well, yeah, probably can." I didn't say another word. And after a few minutes hesitation, he said, "To hell with you, Hibbs," and hung up.
Feynman broke his policy, and within days of the accident, he had joined the inquiry in Washington. The investigation was led by William Rogers, an ex-Secretary of State and the ultimate Washington insider. His formal bureaucratic approach was the polar opposite of the freewheeling maverick professor.
Mr. Rogers, he knew nothing about it. I had been on accident boards before, and I took the opportunity. I said, hey, I just did one of these investigations. Would you like to see it? And I think reluctantly, Rogers said, yeah, okay, you can show it to us, but we're not going to do it that way. And so I went through this very logical step-by-step process of how you investigate a space accident. And Rogers said, no, we don't have the technical capability to do that. And that's when Feynman butted in. He said, no, I like that. I think that's a smart way to go.
For Feynman and the chairman, it was the beginning of a poor relationship. But for the professor and the Air Force general, it was the start of a close friendship.
And he just was the smartest guy in the world. And he had a reputation for integrity. You know, he's the most honest guy in the world. He didn't accept something unless he really could prove it.
The two men began touring the US, visiting NASA sites where the shuttle was made, questioning the engineers and managers.
In the process of speaking to the engineers, you realize, wow, some of them won't talk to me right now because the managers are in the room, you know. It wasn't simply a technical puzzle. There was a human puzzle going on, too.
Writing home to Michelle and Gwyneth, Feynman expressed his frustration and excitement at his hunt for the truth.
Dearest Gwyneth and Michelle, this is the first time I have had time to write to you. I already smell certain rats that I will not forget because I just love the smell of rats, for it is the spore of exciting adventure.
But there was a problem. NASA managers didn't want to reveal the full extent of their knowledge. The result was a smokescreen.
NASA wanted to control everything that they gave to the commission and actually withheld things. They didn't lie, but they certainly didn't go around blabbing the truth either.
What Feynman didn't know was that General Katina had a secret source inside NASA. Sally Ride was America's first woman in space and another commission member. She privately told the general that NASA had long had doubts about how the rubber O-rings, the seals in the shuttle's solid rocket boosters, worked in the cold. And the temperature on the morning of the launch had been below freezing. The general needed to get this information to Feynman without compromising his source. The chance came after supper one evening at Kutina's house. The general restored classic cars.
I took him out in the garage to show him the car, and Feynman really isn't interested in cars. So we walked around the car, and I showed him the interior, and I showed him where the engine was. And Feynman looked at my workbench, and he sees a couple carburetors out there. And he says, Katina, what are those carburetors? And I said, oh, they're from the Opal, and I keep one put together, and then one I take apart and clean. And then the thought came to me, I needed to get the idea of cold and O-rings and leakage across. I said, you know, Professor, these doggone carburetors have O-rings and they leak when they're cold.
Feynman had his answer. And he also had an inspired idea about how to convey it to the world's press.
From that and the various things that you told me about the need for resilience and the lack of resilience.
When the commission next met, he began questioning senior engineers about the effect of cold on the O-rings on the morning of the launch. Their replies were evasive, denying that temperature could have had an effect.
Before the event, from information that was available and understanding that was available, was it fully appreciated everywhere that this seal would become unsatisfactory at some temperature, and was there some sort of a suggestion of a temperature at which The SRB, I guess you call it,
Yes, sir.
shouldn't be run.
It was the judgment that under the conditions that we would see on launch day, given the configuration that we were in, that the seal would function at that temperature. That was the final judgment.
It was Feynman's chance. He decided to use the power of a classic science demonstration.
During the hearings, they had that actual O-ring joint, and we're passing it up the road. It goes to Feynman. I'm sitting to his left, and I hand it to him, and he puts it down. And then he goes into his pocket and pulls out the pliers and the hose clamp and a screwdriver and takes the joint apart, pulls out the piece of rubber O-ring, puts the clamp on it, and then I know what he's going to do. He sees the ice water, and he swears it was just kind of an accident. He got this idea, wait a minute, I know how I can get data on how rubber is when it's cold.
He clamped a piece of rubber and put it in a beaker full of ice water.
Well, I took the stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
The O-rings, which were supposed to create a seal around the solid boosters, had got so cold they'd lost their ability to flex and to fill the gap between the boosters. And that's why the fuel had leaked and the shuttle had exploded.
Feynman had nailed once and for all that the cold could have been the cause of the shuttle's failure just 73 seconds after launch.
It really was a turning point in the investigation. It couldn't be ignored.
In the summer of 1986, the Commission's report was submitted. In its appendix, Feynman added a stark reminder about the limits of science.
His last recommendation, I think, was really summed it up in one simple paragraph. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled.
I remember it was very hard on him. He was just exhausted. He came over, he says, came over to tell you that my cancer's come back again. Doesn't look too good. So I don't know what we talked about. And I don't know how I got off on the subject. I said, I've been thinking about an invariant in turbulent flow. He said, what do you mean? I explained a little bit what it was all about. An invariant, yeah. I said, well, under these such and such conditions. He says, let's see. So I had a notebook there. He took the notebook and he wrote it all down, step by step. I think it took 13 steps to get to that. He says, yes, that's true. It is an invariant. Then he says, you got me thinking about physics again. I can go home now.
Feynman went into hospital for the last time in February 1988. His kidneys were failing, and he decided he didn't want to go through with dialysis to prolong his suffering.
And I still sort of thought, no, this isn't the way it is. But he was able to handle a lot of physical difficulties as long as his mind was sharp.
When a person is dying, their hands move a little. And the nurse who was there says he's not trying to communicate, that's just natural. And he raised his hands like this, and he went like this, which, if you know it, is the symbol that a magician gives when he's going to do a trick, okay? And he went He was communicating, again, of his observations of the world. The doctors were wrong. He could hear. He could move if he tried hard enough. And he could hear and understand what was being said. And those were his last words.
Richard Feynman died on the 15th of February 1988 in hospital in Los Angeles at the age of just 69.
When I took my last walk with Richard Feynman, he was telling me a bunch of funny stories, but I realized the message behind the stories was that he was about to die of cancer, and I got very sad. And he noticed it, and he asked me what's wrong. And I said, I'm sad because I'm realizing that you're about to die. And he said, yeah, that bugs me sometimes too. But not as much as you think, he said, because you realize that at some point in your life, you've told a lot of stories, and those stories are going to stay around even after you're gone.
Today, over 25 years since his death, Feynman's prophecy has more truth than he could ever have imagined. Through an invention that hadn't been created when he died, his stories do live on. Because through their reimagining on the World Wide Web, a new generation is discovering the delights of time with Feynman.
It's fantastic to just be able to Google Feynman, Richard Feynman, you know, any kind of variation, and there it is. You know, you have a lot of stuff out there.
I see my father referenced in popular culture a lot more now than when he was alive.
I have a friend who's an artist, and has sometimes taken a view which I don't agree with very well. He'll hold up a flower and say, look how beautiful it is, and I'll agree. And he says, you see, as I as an artist can see how beautiful this is, but you as a scientist take this all apart and it becomes a dull thing. And I think that he's kind of nutty.
You wonder what Feynman would have made of the internet. And I think he would really, really like the idea that he's spread all over the world in clips, short and long, on the internet for maybe all time. I think he'd like that. You know, then you just touch it like this.
A poet, I think it is.
And you bring his voice right back, you know.
The whole universe
is in a glass of wine. I don't know. I don't think we'll ever know in what sense he meant that. For the poets don't write to be understood.
I know what I'll remember him for being a good brother and a good person.
He wasn't just the scientist, he wasn't just the artist, he wasn't just the educator.
He was physics with a human face. You know, he showed that in order to be a top-ranked physicist, you can still be a human being. So I think that's a very important legacy to people who want to do science. You know, it's a human endeavor, and he showed that.
Has Richard Feynman inspired you to follow your own path in life? Join the Open University to explore your options and find out more about how he revolutionised the face of physics. Go to bbc.co.uk/Feynman and follow the links to the Open University.
Mock the Week looks back at Royals next on BBC Two, then a culture show special on the Smiths at 11.